Good morning. Today's lab, we are going to be looking at friction. So we've been talking about friction in class, in lecture, and what we want to do is take a look at some measurements of kinetic and static friction, and from those go in and calculate some coefficients of kinetic and static friction. So, quick review here. This is what the setup will look like. We're going to have a block on one of our tables here in the lab room, and we're going to let that block slide across the table. Now we have different materials here. Here's what one of the blocks looks like. So this is just a wood surface, and we're actually going to be running these along one of the wood surfaces in the lab room. So, of course, the frictional measurements that we get and the coefficients of friction are going to depend on these specific materials that we're working with. So the lab tabletops are some kind of an engineered wood material, and this just looks like a piece of wood that's been smoothed down over years of sliding across tables. Anyway, that's what this block looks like. Now there's some other materials here. This is oak leather, it says. So this block actually has a piece of this oak leather material that has been glued, adhered onto the bottom. So we'd be testing this material. Again, the other side of that friction force would be one of our tabletops here in the lab room. Here's another piece of material. This is called neolite, which is some kind of a synthetic material, and again, we've got blocks that have that on the bottom. Now, we have like 6 different materials. You don't have to do measurements on all of these, so pick 2 of these. I went ahead and picked, for my measurements, I think what I'm going to try is just the plain old wood, and then I decided to go with this neolite. So anyway, what we'll do is we'll set these on the tabletop, and then we will attach a string onto this, and we'll pull on the string. Now, the force diagrams look something like this. Here is the block on the tabletop. There's a gravitational force pulling down on it. That sets up a normal contact force between the block and the tabletop. So that's going to be the normal contact force along here. We're going to pull on that string with some amount of tension, and then we're going to determine from that how much of a static friction force there is. Now remember, when we're measuring coefficients of static friction, that means that the static frictional force is right at its maximum. So what we're going to do is we're going to pull a little bit, and then we're going to pull a little harder, we're going to pull a little harder. The idea is to gradually increase this tension until we hit kind of the breaking point, the point where the static friction can no longer offset this tension and the object begins to slide. So now right at that point, what we can state then is that the static frictional force is equal to the tension. Right? For static friction, there is no sliding taking place. That says the speed of the block relative to the table is going to be 0, and that says the static friction force is given by tension. Now, the other force diagram here shows us that, well, we're going to have a hanger hanging over the edge. There's our pulley right here. We're going to have a hanger with some weights on it, and we can add and subtract weights as needed. So right now, let's see, we've worked with these hangers before. The hanger itself is like 50 grams, and then, here's a 100-gram sample, so here's another 100 grams. Now, just to check the masses on these, we can also set up a scale. So when we take a look at the detailed setup, we'll see where the scale is located. Here's a 50. They also come in 20s, 10s, 5s, 2s, and 1s. So potentially, we could really fine-tune the tension here. Now, what happens with friction, and we talked about this in lecture also, friction's complicated. So it's not, with the surfaces we're dealing with, there's enough variability in the surfaces that it's very difficult to reproduce a measurement down to the level of 20 grams, or even 50 grams, or sometimes 100 grams. And so, you know, we're going to recognize that that's what's going on. What I mean by that is at one placement, we might get some number in terms of the maximum tension. If we try and replicate that number, if we just set everything up the very same way, we could get something that's quite different, okay, from one measurement to the next. Now, there is enough consistency that we should be able to pick up a pattern. But again, it's not something that we're going to be able to measure right down to individual grams that we hang on the hangers. That doesn't happen. So let's see, static friction, velocity here is 0. The normal force is going to be given by m1 over g, and then the coefficients of frictions are defined in terms of frictional force divided by normal force, and then we can get a coefficient from that. Now, we've been treating these coefficients of friction as if they're a fixed constant, and in lab today we can check and see if that's a reasonable approximation or not. The way we're going to do that is we're going to vary the normal force. So let's say that I've got this block set up. It's on the surface. I'm pulling on it. And right now, it turns out these blocks are about somewhere between 500, 600, 700 grams, depending on which material we're looking at. I think I did some quick measurements earlier, and the wood block was like 520 grams, and the neolite block was like 700 and something. So to increase the normal force, what we'll do is we'll do a measurement here with the block by itself. That's going to be, let's say, somewhere around 500, although this is actually heavier. And then what we'll do is we'll add 500 grams. And so we have these other weights. So when I add that on, I've increased the normal force. The normal contact between the surfaces now is larger because we've got this additional gravitational force pushing down, and it's going to push those surfaces together more firmly. Now, our prediction from class is that as the normal force goes up, the frictional force, we've been assuming, goes up proportionally, and the lab is going to enable us to go in and see if that assumption actually pans out in reality. So I can increase the normal force. I can go 500 grams higher, right? And then I can take the 500 out and put in 1,000. That's going to take me, so what we're doing is we're going up in increments, roughly, of 500 grams. And what I'm at right now is somewhere around 2,000. This is going to put us somewhere around 2,500. And then to go to the 3,000, I mean, we could add some more of these blocks, but let's use the brick. So the bricks are around 2,500. So the brick, together with the block, are going to give us something around 3,000 grams. So what we'll do is we'll get, we'll get 6 data points. And we're going to have, you know, a wide range of different normal forces. So we're starting off at, let's see, this is like half a kilogram time. This is going to be like 5 newtons, 10 newtons, 15, 20, 25, 30. So we're going to have a range, a pretty wide range of normal forces. So our data points could be somewhere around 5, 10, 15, 20, 25, 30 newtons. Now what we want to find out is, as the normal force increases, does the frictional force increase proportionally? So we'll do that in 2 different ways. First of all, we've got this data table where I've listed the values for M1. And then what we have to do is go in and do a series of measurements of M2. So I've got a setup going back here on one of the tables. We'll take a look at that setup, but I'm going to go in now and take measurements of M2. Now, what are those going to look like? for the static case, and what would they look like for kinetic? We have yet to talk about the details of the kinetic. Well, for the static case, what I'm doing is I'm steadily increasing the tension by taking different objects, different weights, different masses, and adding them until the static friction can no longer keep up. At that point, sliding will begin, and whatever amount we have on at that time, we can carry that over to the scale, set it on the scale, not on the block here, but set it on our scale. And from that, we can write down a number of how large M2 became. So we got M1, that's determined up front. We're going to take these 6 data points, or something similar to those, and then we will experimentally determine for the static friction, what are the highest values of M2? From that, we can calculate the frictional force. From that, we can also, let's see, M2 is going to give us the frictional force. M1 will allow us to determine the normal force. And then finally, we can take the ratios, and that will give us the coefficient. Now, there's going to be a data table for static measurements, and there will be a corresponding data table for kinetic measurements. Now, kinetic friction, let's see. How do we have to change our force diagram? And we don't. And here's the reason why. When we're doing the kinetic measurements, we are going to need to have the block moving because we want to be sampling the kinetic friction. Well, if we are able to have the block move at constant velocity, that would say that the tension matches the kinetic frictional force. So what we can do is we can do a set of static measurements, and then when we're ready to do the kinetic friction, here are the adjustments I make. I take out the S for static and I put in a K for kinetic. And what we do is instead of being at rest, now we'll say it's moving with a constant velocity. So if we can adjust the masses so that it slides across the table with a constant velocity, then all the formulas work the very same way. So that's going to simplify the procedures. Now, the thing we have to watch for here is we have to estimate constant velocity. So we don't have any complicated timing devices watching it slide across. But typically what happens is this. What you can do for these measurements is, let's say we put some mass on there. We bring M2 up to some value. Now, since it's kinetic friction that we're measuring now, I've got to push this. So I'm not measuring static anymore, so I'll give it a push. And I'll give it an initial velocity. Then the question becomes, as it moves across the table, is it picking up speed? Is it losing speed? Or is it going across the table at a fairly constant velocity? And what you'll find in the measurements is, again, it doesn't come right down to plus or minus 1 gram or 5 grams, but by the time you get up to kind of plus or minus maybe 20 grams, within that range, if I go 20 grams higher, for example, I can obviously see that it's picking up speed. If I go 20 grams lower, I can see that it's slowing down. So what I'm looking for is something in the middle. And we'll see some demonstrations of that. So I'll include a video taking a look at some of those measurements. So that's the idea, is that for the static case, we place this at some location, we gradually increase the tension here until this breaks free, and at that moment we take whatever value we've got for M2, we write it into the data table. At that point, what we're doing is we're adding maybe 5 or 10 grams at a time, and that's the best we're going to be able to do. If we can get a measurement within 5 or 10 grams, that's perfectly fine for us. In the kinetic case, a lot of times students are hesitant about this. They go, you mean I have to push this? You go, yeah, it's kinetic friction. And so what we want to do is give it an initial velocity So go ahead and give it an initial velocity by giving it a push. And then the question becomes, once you've given it that initial speed, is it speeding up, is it slowing down, or is it maintaining constant velocity across the table? And we want to take the measurements when the velocity across the table appears, as best we can tell, to be constant. All right, so I think we've got all this sorted out. So again, we'll have a data table we'll have two data tables. One for the static measurements, one for the, we're going to have 4 data tables. I take that back. We've got 2 different materials. So for the wood, we will have a data table for static and a data table for kinetic. When we switch over and take a look at the neolite, again, we'll have a static data table and a kinetic data table. So it sounds like 4 data tables altogether. Ooh, the graphs. It wouldn't be physics lab if we didn't have a graph. Graphs are really important. I know I keep saying this, but we are going to try and, not every week, but whenever we can, get a useful graph in there that we're going to put one in there so you guys can practice developing and generating these graphs. Again, my advice always is make sure that you are involved in creating all of the graphs. Don't just let other people in your lab group put the graphs together. When we have midterms or the final exams, there are going to be questions that ask you to put together a graph, and so you want to practice drawing graphs, labeling the graphs, making sure that you have units. You want to practice all those skills. When you turn in your lab reports, I'm going to provide feedback, suggestions on how the graphs could be improved. Make sure that you're looking at the feedback on the lab reports so that you can develop those skills. That's going to help out with future lab reports, and potentially it's going to help out with the midterms and with the final. All right, so here's the graph. We're going to do frictional force versus normal force. Now, we want to do static and kinetic measurements. We can do that on the same graph. So I'm going to say one graph for each material. So here's the neolite. That's going to have a graph for that. And then we're going to have a graph for the wood. There's going to be a set of static data, and there's going to be a set of kinetic data. And what I've done here is I've labeled those using different colors. And when you go into, if you're doing the graphs by hand or if you're doing the graphs by computer generating them, either of those approaches work. And what you want to do is get the data plotted. As always, I keep saying every lab, make sure that the data is clearly designated on the graph. Don't turn the data into a line. Don't hide the data. So the data should be listed as data points. This is where we took the data. These are the values that we got. And then there are what we call fit lines. Now, there's going to be a fit line for the kinetic data, and there's going to be a fit line for the static data. If you can do these both on the same graph, I think that's useful, but it's not required. If you want to do 2 separate graphs for each material, that's also fine. But play around with whatever graphics software you're using. If this is Excel, for example, play around with the menus. This is a good time where you can work together with other people in your lab groups and get suggestions or learn how to present the data and get these fit lines. Now, in this case, the fit lines that we come up with, we're going to have the fit lines be linear. These are going to be straight lines. They're also going to be straight lines that go through the origin. And that's because that's how we're defining coefficients of friction. Now, if we can find a line that roughly approximates all of the data points, that would indicate that the model we're using, where we treat the coefficients of friction as being a constant, are pretty reliable. If the data just doesn't line up at all, then we might want to the takeaway could be that the model we're using is too simplistic. It's not reliably representing what's going on. Now remember, friction is complicated, so from one placement to the next, you know, if I set this on the table, and then I pick it up and I set it down again, you could end up with different measurements of friction, even from one placement to the next. So we'll see. We'll see what the data points look like. All right, now on this graph, you know, every time we do a graph, we talk about the axes, and then often what we'll find when we do these fit lines is the fit lines mean something. They have some significance to them. And in this case, if you go back and look at the formulas, you realize, oh, the slopes are the coefficients of friction. So if I can get a line, a straight line, you know, colleagues in the math department always tell me that's redundant. Lines are straight by definition. I should not be saying straight line, but I'm going to keep saying straight line, I guess. So, so if I take this straight line that I've used to fit the kinetic data, the slope of that is going to give me a coefficient of kinetic friction. Similarly, for the static data, I'll end up with a coefficient of static friction. Okay, so make sure you're understanding the force diagrams, the formulas we're using, the requirements as to how we're going to collect the data. What does it mean to collect data on static friction? And what does it mean to collect data on kinetic friction? For the kinetic, we need to estimate a constant velocity. We have to adjust the values of m2 such that the velocity, as best we can tell, is constant across the surface. Of course, for static, we want things not to have any velocity. Okay, so let's see. 4 data tables, 2 or 4 graphs, depending on how you do this. And then the results table. So here are the results tables. Again, I picked wood and neolite. Now what I really should be saying, let me write this in a little more detail. Let's say wood on the tabletop, and let me say neolite along the table. So it's really the combination of surfaces that we're analyzing. All right, so we'll get a set of, you know, we'll take a look at the couple ways we could average here. So I could average all the values for the coefficient, or I could just get the line from the graph. I'm thinking this is probably the best way to do it, is just get the slope of these 2 lines and record those as mu sub s and mu sub k for the 2 different materials. All right, I got some more stuff up here too, I guess. I did bring one of the pulleys. I think in a previous lab, I never showed the pulleys in operation. So here's what the pulley looks like. Now, they're not massless. They're pretty low mass, and they have pretty low friction. So it does eventually, there's a little friction here. So, you know, that's going to be part of the limitation, is we have not accounted for the mass in the pulley. Oh, it doesn't make any difference anyway, right? Because we're only looking at constant velocities. Okay, good. And then the friction doesn't matter for this static case, but it will, no, it does make a difference, doesn't it? Yeah, so the friction could affect both the static and the kinetic measurements. So, and the friction we're talking about here is the friction in the hub, not along the circumference. We expect friction along the circumference where the string is running, but in the hub, we're treating the hub as if it's frictionless. Okay, so the mass of the pulley, not an issue. It's an inertial effect, but the friction in the hub will end up making a difference. I guess that's it. We got the blocks, we got the weights, we have the pulleys, and we have the hangers, which are going to be our M2 measurements. So let's take a look and see what the setups look like and see what taking measurements is going to look like. This is the setup we have for the friction lab. If you take a look, there's the pulley right there. We've got the string attached to the block over on this side. And then what I've got here is I have those weights. So we're getting ready to set those onto the block and adjust the normal forces. Then over here on the table, what I've done is I've lined up a bunch of different weights that I can use. And so I've got a stack of 200 grams, 100, 50s, a bunch of 20s, 10s, 5s, 2s, and 1s. Now, I'm not getting down to the resolution where I'm putting on 1 gram at a time. I'm really just getting down to usually the 10s. By stacking a bunch of 10s on, at some point I'm going to be able to get a fine enough resolution where I really can't tell the difference. Stacking an additional 10 on may not be all that noticeable. But that's it. Let me take also a couple of pictures. And here's the scale. So the scale is right here. So here's an example of what the measurements are going to look like. So what I've got right now is, if we take a look at the block, we've got a wood block. Right now I've got 1,000 kilograms sitting on top of the wood block. And what I have is I've got 400 grams hanging over from the pulley. Now, if this is a static measurement, the idea would be to add mass to this side. Now, right now I'm going to try adding some 50s. So I'm going to add 50 grams on. So far, so good. Let me move this. Maybe that's going to help with viewing. I'm getting a little nervous, so I think what I'm going to do is I'm going to drop down and start using some 20 grams. So there's 20, there's 20 more, there's 20 more. Uh-oh, maybe I'm going to run out of all my 20s. So you kind of have to judge how this is all going to work. I got a few 20s left here. Let me put a 20 on here. The static friction is still holding up. So I've still got the static friction holding things in place. I'm going to move on to my stack of 10s. And here I am, putting on my stack of 10s. Now again, you'll notice what I'm trying to do is put these on carefully, pausing just momentarily. Ooh, I'm almost out of my stack of... Oh, there it goes. So you could see what happened with this particular collection of weights, which are kind of scattered all over the floor right now, is when I first put that last 10 gram on, it stayed in place. And while I was getting ready to pick up another 10 and put on, at some point the static friction was not enough. And so I'm thinking that's a good measurement. So what I'm going to do now is I'm going to collect everything that was on there. So here we are, just lifting all of these weights off the floor. Now, I've got the scale set up here, right? So what I can do now is I can just take a look at my scale, and I'm going to take everything that was on there. I'll take the other ones that kind of, you heard the crash, the stuff that fell off. And what this is at is 710 grams. And so this is static friction for wood was the material. And that's what a static measurement looked like. And I'm ending up with 710 grams. That is where I found the limit of the static friction. Now let's do this also, as long as we're right here. Put the scale out of the way. What I'm going to do is I'm going to bring back my hanger. I'm going to reset everything. What would a kinetic measurement look like? Now, kinetic friction, we're expecting, in most cases, the kinetic friction is going to be lower than the static friction. And so for that, I'm going to take off these 20s, I'm going to take off this 50, and add a couple 200s on here. I think what I'm going to do is, I'm going to try starting at 300 grams. And so here is a 300 gram weight, 300 grams of mass that's setting up tension in my string. Now remember, this is a kinetic measurement, so I get to push the object. So I'm going to give it an initial velocity. Okay, what's happening here? Well, I give it an initial velocity, but look, it slows down and stops. So that says that I have not yet reached the point where the tension is matching the kinetic friction. When I push this, the friction definitely goes kinetic. There's enough kinetic friction that it slows it down and stops it. So I need to put more mass onto this. So I'm gonna reset this back at my starting point. You know, something I should point out here too, there's always a little bit of a concern is as we do a whole series of measurements here, does the surface actually get smoothed out a little bit? And there's some indication that that is happening. A couple of other things that I could point to here. Notice how I've set up the pulley. So I anchored everything down with this clamp. These are tightened a lot so that it doesn't get pulled side to side. And then what I've done is I've checked alignments. The force diagram we looked at tells me that the tension needs to be parallel to the surface. So I've adjusted the pulley in a way where the string is running horizontally. So I want the setup to match what we've done in the force diagram because all the equations we're using are based on the force diagram. So I'm checking alignment on the string. It looks very horizontal. I'm tightening everything. I'm looking to see if things are being torsioned. And it looks pretty good. You know, as and this could actually be turned just a touch. Don't know if that's a good idea at this point. There. Okay, that alignment looks good. And so alignments are going to be important with this also. All right, we determined that the mass I have on here right now, it's not enough. So what I'm going to do, and it didn't look like, I'm going to add, maybe I'll add 100. 100 seems like maybe a lot. But I'm going to add 100 to this side and give it another push. Boy, that looks pretty constant. That actually looked pretty good. I'm going to come back and I'm going to try that again. What do you think? Constant? I'm going to add 20 grams on. Let's do this. Let's add 20, maybe 50 grams. I'm going to bring this back to our starting point. And let me add on, I'm going to add 50. That seems like maybe a lot. But so let's try this again. Now that seemed like it was speeding up. Okay, it's a bit of a judgment call, but it did seem like there was kind of a steady increase. We can try that again and see. So I'm thinking the 50 was too much. So again, see how it seems like it's picking up speed. I'm going to take off the 50 that I put on there, and I'm going to replace it. I might try a 20. Now, when I'm getting down to the level of 20s, or certainly by the time I'm getting down to 10 grams, that's about the best we're going to be doing. So I'm going to give this a push. That actually looked better. What do you guys think? It seemed to me like it was able to maintain a more steady speed. Okay, there I've caught something. So let me see if I can, maybe something on the, I think it's dragging on something right now. Let me see if I can check the surfaces, sweep off any dust. Okay, here we go. Yeah, it seems more steady at this particular point. Again, it's kind of caught on something a little bit on the underside, but that's the idea. So the idea here is, okay, smoothing out my surface. I'll try this one more time, but I think we're there. I think this is going to be a perfectly good measurement. Okay, so let's check and see what we've got. Again, what I can do is I don't have to take all these off and count they have numbers listed. So this says 20, but what I can do is, to get a faster and a more reliable number, I can just take it over and set it on the scales. Now it does say it's at 420. So the numbers check out 100, 200, 300, 420. So, and the scales are reading 420. So that's the measurement that we have for this. And I'm just looking, I did a previous set of measurements here. So I've actually run all the measurements. So I've done those. And the number I got before, surprisingly, was 419. The number I had before for the static was 769. So the static number that we just got here was actually fairly different, but the it was different by 60 grams or something. The kinetic was within just a few grams. If we redid this, we would probably see fluctuations of easily fluctuations of 20 or 30 grams probably for the kinetic, and 60 or more grams for the static. But by taking a number of data points, what we're going to be able to do is come up with graphs that will kind of smooth out the effects. So again, what we'll eventually be looking for from the graphs is it kind of plausible that there's one line that represents kind of the overall effect. Does one line represent the data pretty well? And if it does, then we can say, yeah, this coefficient of friction model, it works pretty good. So we'll see. We'll run the numbers and see how this works out. If you guys have any questions, let me know.